Hello and good evening. Thank you for watching my video. Today I will be examining the shift register, more specifically the 74HC595, and this is a very generic shift register, and it is serial in and parallel out. So it takes in 1 bit of data and it sends it out on 8 different lines. Well, that's a byte of information, isn't it? I will get to looking at the data sheet in a moment, but first I will informally discuss the pinouts on this chip. So this came in a set of attached PCB mounted ICs, so I just broke one off. And this is not the dual inline package, this is surface mount. So this is a very small little module. So here is where the serial data comes in, 1 bit at a time. And of course, in digital electronics, that means a 5-volt high signal or a ground or low signal. Here are the power pins, ground and VCC. Once again, these are the output. And it tends to shift the bits in here, and they shift out here. I want to say most significant bit and least significant bit. I'm actually not sure. I don't want to say that incorrectly in my video. Once again, I will get to looking at the data sheet. There is a slight variation in what these pins are called in the data sheet. To me, some of this is a little more intuitively described as the pinouts. It may not completely match up with what the data sheet calls them. So here's the VCC, or the positive, and the negative, the ground, power supply pins. And here is a shot of the back of the board. And you can see that a lot of these pins are just tied to the other side of this PCB board. So here is VCC is the bottom one, and ground is just above. I'm just looking at this myself. So here's the VCC. There's a bit of a gap between the darker red and the lighter pink color. So this is VCC, and so is this. And it looks to me like these ground pinouts are actually connected to this field of pink, so it looks like the ground connections are all connected to this field here, whatever you call that. And once again, a lot of these pins are connected to each other on the back side of the board, and that's because they're mostly the same thing. L clock, L clock, 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 OE, OE, reset, and reset. Now these are different. This is the serial in, and this is the serial out. These are two different pins, as can even be seen here. So these 4 pins here are connected on the back of the board to these 4 here, likewise with the power pins. But these pins are different. Most of the pins on this side are the parallel out data lines. But there's one more here. Here's A. It's actually not connected to this side. It goes up. And what's that? I thought maybe I could just hook up some digital push button switches and play around with it. See if I could get it working on my own without any reference material. Well, I was wrong, because there are a few things to understand about getting this chip working. So this reset pin, which is reset when it goes too low, has to be sent to the +5 volt rail. So this has to be tied to positive high, and it's reset with a low signal. This is the output enable pin, and it's going to be tied to ground because we do want the output enabled, which will basically just send out the data and light up, say, LEDs if you have them connected to these parallel lines going this way. So this pin should be tied to ground if you want to see the output. And if you send it a high, then it'll make this not visible anymore. So I will just restate. To get your chip working, tie this reset pin to +5 volts. And if you want to be able to see what your parallel data lines are doing, then tie this one to ground. As for the bits of data that it takes in, you want some way to switch between highs and lows. So a slide switch might be great for this. I have a push button, but a slide switch might work even better. Let's just say you send 5 volts in here. So you're sending high bits in. Then you're going to clock in those bits using these 2 pins. Let's just suppose that clocked into the memory of this chip are all lows, and the parallel output is sending these all low signals. And we want to change that. We want to send in all high bits. So we would put a positive 5 volt signal on the serial in, and then we would clock in 8 bits into the memory. So what you would do is you would push this clock button, or this same one here, this clock button, you would push it 8 times. 1, 2, 3, 4, 5, 6, 7, 8, assuming you had maybe a push button. And then to spit that information out on these 8 parallel data lines, you would clock this pin once. I believe that a low to high signal, when your push button is sending a high signal when it's pressed, if you press it 8 times, this should clock in 8 bits of data, and then this will spit out your data on the parallel lines when you push it once. But I believe this L clock is clocked in from a high to low. Hopefully I have that correct. Alright, once again, very informal. I'm going to look at the data sheet. I believe that my chip is fairly close to this data sheet, but there are different versions of the chip coming in different package sizes. Okay, so it features, well, once again, we're talking about the HC595 8-bit shift register with 3 state output registers, and it features an 8-bit serial in parallel out shift, wide operating voltage range between 2 and 6 volts. I'm currently using 5 volts. It has D-type storage registers. Separate clocks are provided for both the shift and storage register. The shift register has a direct overriding clear, SR clear input, serial input, SER, and serial outputs for cascading. So yes, you can hook these chips up one to another. If you have more than one chip, you can hook them up end to end, and you can cascade bits of data from one chip to the next. Maybe you've seen videos of this. When the output enable input is high, the outputs are in the high impedance state. Well, to enable the output, you have to send it a low signal. I'm not sure that's what that's saying. It's kind of remarking on something else, the high impedance state. Here is the functional block diagram. But here are the pinouts. So here are your parallel data line pins, B down to H, and A is actually on the other side of the board. This QH pin is the serial out, so if you want to cascade bits of data to the same chip, just more additional chips, you would use this pin 9. On my chip, these were called L clock and clock. They're calling these ones R clock and SR clock. This is your serial in line here. And on my module, they're calling this serial out, QH.
Alright, so I will be methodical in explaining this. So this serial in line on this chip down here is actually connected to this push button here, which is actually sent out to these two female headers. These push buttons actually control a normally low and a normally high signal. When I push the button, it swaps the two signals. I made a video on this module. It's also available on my channel. What's this line doing? So anyway, this line here is the serial in pin. And as you can see, I can control the state of it. So if I want to send all high bits in, I'll just leave it as it is. If I want to send low bits in, the wires coming out of this header strip here, I can change the state of it there. This second, well, I won't talk about the yellow one first. I'll talk about these green ones. This third push button. I have this third push button hooked up to the clock pin. So currently we're sending in high bits on the serial in line. Let me clear all this. Okay, say we're sending in high bits right now. So say I want to clock in 7 high bits. I hit the clock pin, the clock one, 7 times for a signal from low to high. 7 times. 1, 2, 3, 4, 5, 6, 7. And that is logged into the memory of the chip. And when I want to spit it out, I send the L clock. The L clock pin from high to low. Watch, I'm going to push it once. And there's my 7 bits. This last LED is not lit up. Let's clear that. Currently we're sending in low bits. 1, 2, 3, 4, 5, 6, 7, 8. Those are clocked into the memory. When I want to spit it out, I hit that L clock pin from a signal from high to low. And it clears it. This button doesn't work so well. I have to push it hard. This down here, this line out, which I can send from high to low or low to high, is the output enable bit. Let's get some bits lit up here. Okay, so we have a combination of ones and zeros. I know it's a little hard to see. Maybe that's better. So this output enable pin, what did I say that was? I can't get it to focus, but this is hooked up to the output enable, which is normally held low. And we send it a high, it won't enable the output. So if the output enable is held low, which it is here, it'll show the data on the parallel lines. If we send it a high, it'll just clear it. So you don't really need a digital input on the output enable pin if you like to see what's going on. generally just send the output enable pin low. The reset pin I don't have hooked up. Oh yeah, I do. Where am I? Oh yeah, this is the reset pin line. I have this orange jumper cable here, and I just set it as high because you reset the chip with a low signal. So if you want your shift register to work, you need to have the reset pin tied to a high signal, which I do. Okay, I repeated myself a lot throughout the process. Hopefully that's not annoying, but thank you for watching, and I hope that helps you. Hey buddy, how's it going? What are you doing?